Hi, my name is Nastianowski. We're going through Monoidal category theory. We're up to section 4.5. Okay, so let's just remember, chapter 4 is all about how categories relate with each other. 4.1 was about functors, 4.2 was natural transformations, 4.3 was equivalence of categories, 4.4 was a big one, adjunctions, okay, and now we need some tools, okay, and so this is exponentiation and common categories. Basically, we're going to see how to, these are operations on categories. Take two categories and you get another category, and common categories are very interesting. They're ways of making the morphisms of one object, of one category, into the objects of another category. So we'll see how to do this, and we'll see why this is very important. Okay, so exponentiation is extremely important. We saw one operation on categories, namely take one category, take another category, you could take the product of them. Okay, this is something else. So let's remember, let's go back to sets for a second. We always get our intuition of sets. Given one set S, given another set S, T, you can look at the Hom from set, namely the function set. We write this also as T to the S, okay? So what is this? This is the set of all functions from S to T. Very nice. Well, guess what? I want the same thing with categories. So here's the idea. Given a category A and a category B, I want to look at Hom, not in set, as we had before, but in cat, okay, of Hom A comma B, which is, we write this also as B to the A. Okay, that's another way of writing it, B to the A, hence the word exponentiation. Okay, and the idea is, what is this? This is, I'll just say, collection of functors from here to here. This is the collection of sets of functions from here to here. So now we're talking about categories. So this is the collection of functors from here to here. 1 second, it's more than just a collection because it has more structure than just a set. Because besides just functors, there are natural transformations between these, between all the functors from A to B. And so if you look at the collection of functors and natural transformations, you get a category. So this is in fact a category, okay, and this is called a function set. This is called a function set. And so this is going to be called a functor category. Okay, and we're going to spend a lot of time going through different examples of these and then see how these different functor categories relate with each other, and we're going to have a lot of fun. Okay, so let's do a ton of examples. Okay, so the simplest example is, let's say you have a category B and you look at this functor category, where one is the one object category with just the identity. Okay, so let's think about this. The functor from here to here picks out an object of B, okay? And the natural transformations are if you have one functor which picks out a an element of B, and you have another functor which picks out an element of B. A natural transformation for that is basically a morphism for this single object here that goes from this object to this object. So basically, that's a morphism in B. In other words, this is isomorphic. This is a category of functors and natural transformations, but it's isomorphic to the category B itself, by itself. Okay? Okay, it's not equal. Okay, there's a map from here to here, there's a map from here to here. They're not equal. This is a category of functors and natural transformations. This is just a regular category, but they can be made isomorphic. Okay, good. Let's do another one. Take the category B and look at this category. Let's just remember what this category is. This is the category with two objects and no morphism in between them. Just this is the category, so there are identity maps. Very nice. Okay, let's see what this will do. Well, a typical functor from here to here picks out not one object, but two objects here. Okay, and if you have two functors picking out two objects, then a natural transformation for them is simply a morphism in here related to this map with this object, and a morphism in here related to this object. So B to the discrete category of two elements is nothing more than, in other words, it's isomorphic to B cross B. Pairs of objects of B, pairs of morphisms of B. Nothing exciting. Okay, let's do something a little bit more interesting. B to the 2. Okay, this is just another way. I'm just going to write it another way. That's B to the arrow. Okay, and what's this about? Okay, well, let's see. What this is going to do is it's going to pick out an arrow. B1, I'm going to draw this down here, B2. A typical functor from here to here picks out an arrow from here to there. Okay, great. And another typical functor will pick out an arrow from here to there. Okay, great. Now, what's a natural transformation? Well, it's going to be a natural transformation between these two things. Basically, the component of the natural transformation out over here is going to pick out a morphism like this, and the component of the natural, I'm sorry, we're going to call this F, we're going to call this F prime, and the component at this point is going to pick out a natural a morphism over here, so we'll call that G prime. Okay, great. Now, let's do this. If you have two of these, or three of these, and you have a natural transformation like this and a natural transformation like this is going to correspond to a box. This is going to correspond to a box, okay? And in the book I write horizontal, but it's actually vertical composition. So that's a vertical composition, and basically that's going to correspond to doing another thing like B5 and B6 and something like that. Okay, so this is F double prime, and this is G, I don't know, G1, G2, something like that. So placing one box next to each other. So this is called the arrow category of B. Okay, by the way, that's an interesting thing because it makes the objects, I'm sorry, it makes the morphisms of B into the objects of B to the 2. So the morphisms of B become the objects of B to the 2. Okay, great. Okay, let's look at a more sophisticated category, a more sophisticated exponentiation. Okay, let's look at set. Okay, and now, rather than having one arrow between these 2 points, so I'm looking at a particular category, not B, but a particular category set, and now the exponentiation is 2 points, just like before, but now there's 2 maps between them. Okay, now names don't really matter around here. Okay, so I didn't give these names and I didn't give these things names, these objects names, but we might as well do it. So here's a name for these things. So for the objects in this category, we can call this A. I'm sorry, I don't want to do this as a boldface A. I want A, because a boldface A would be a category. I want A, an object. Okay, V, an object. Doesn't matter, I'm calling my category what I want. Okay, we're going to call this map SRC for source. We're going to call this map TRG for target. Okay, and now here's a whole category. Of course, there's identity morphisms, et cetera, composition is whatever it's supposed to be. And this is the category of sets. And now what's this set to this category? And the answer is as follows, very simple. Ready? A is going to pick out a set. V is going to pick out a set. And then there's going to be a map so you're going to have a set f of A. There's a typical functor from here to here. You're going to have a set f of V, okay? And you're going to have a function called f of src, and you can have another function called f of trg, target. Okay, and basically what this is going to be is, you've seen this before, this is a graph. This is a directed graph. Let's go through it. Here's your set of arrows. Here's your set of vertices. Okay, and for every arrow, there's a beginning vertex. For every arrow, there's a target vertex, and you have that. Now, a natural transformation from F to G is a graph homomorphism. A little bit more complicated to see. Okay, so basically, this thing is isomorphic to the category of graphs. Okay, if you want to say equal, I wouldn't be against it. But technically, this is a functor category. This is a things. But it's kind of it's close enough to being equal that if you wrote equal, it wouldn't be terrible. Okay, so the category of graphs. Okay, that's very nice. Okay, so this is a very short way of writing the category of graphs. Okay, let's make this a little bit more complicated, or let's make this diagram category a little bit more complicated. We can do this, labels of V. Okay, so now, I don't know. Okay, so now a functor from this three-element category to this, three-object category to this, to set, is going to pick up a bunch of arrows, going to pick up a bunch of vertices, going to pick up a bunch of labels of vertices. Okay, and basically what this says is every single vertex is going to have a name. Okay, and this gives you the name. So let's call this name of V. Okay, so this is going to be not directed graphs, but directed graphs with labels on the vertices. And we can do the same thing with labels on the arrows. Okay, we can call that name A. Okay, so now we have, not only does every arrow have a source and a target, but every arrow also has a name, and every vertex has a name too. So this is just a more complicated way of looking. This is a variation of graphs, more complicated than that. So this has 1, 2, 3, 4 objects in the category. Okay, great. Let's look at another example. So this is, we need a little bit more room. Okay, take M. M is a one-object category, which is thought of as a monoid. Okay, we have a monoid. Okay, and now let's look at set to the M. Okay, and this is, we've seen this before, this is M sets. Okay, basically what they are is the one object here picks out a set here, okay, and the morphisms, every single morphism, so M is to be thought of as something like this. Lots of little arrows going back and forth from the single object. The morphisms are going to be operations which transform that set. They change that set over and over. Okay, so this is the category of M sets, okay, which we talked about, I think, in chapter 4. And then, of course, there's M set homomorphisms, okay, which are actions, the monoid actions, which are functions that preserve the monoid actions. So every single one of these is going to go. So again, a functor from here to here takes an object here. There's only one object, okay? It picks out a set, and every morphism is from that set. There's going to be f of m, a map from that set to itself. Okay, great. Let's look at two examples of these types of M sets that are very important. Okay, so let's first look at set to the n. Okay, what the hell's n? N is the natural numbers. Okay, so you should think of it as, I'm sorry, it's the natural numbers thought of as one object's category. So I'm going to write it like this. You can write it like this, but this is a little bit more neater. It goes on forever and ever. Okay, great. That's what this natural numbers are. It's a one object category which has the natural numbers in it. Okay, and now a functor from here to here is basically picks out, this one star picks out a set S, and then there's f of 0. And then there's f of 1. And then there's f of 2. And then there's f of 3. Okay. Now, the way to think of this is, I'm sorry, so this has a fancy name, and I'll tell you the fancy name in a second, but basically you have one set, and you have these functions that are changing the elements of the set. Okay? Okay, and so this is called a discrete time. Okay, discrete because the natural numbers are separated. 0, 1, 2, 3, 4. Discrete time dynamical. Good Lord. Dynamical system. A discrete time dynamical system. Dynamical system means it's changing, it's constantly changing. Okay? For every time it changes. What the object is changes. Okay, great. Let's do another example of an M set, which is going to be important. Okay, and that's set to the real numbers. Okay. Okay, think of the real numbers also as a one object category, okay? And now for every r, for every little r, there's a map from S, okay, little r to S, okay? It's hard to describe it because this is countable, and I can start describing it. This is uncountably infinite. I can't even draw two of them. Okay, because there's no two that has it. Okay, so again, the natural numbers and the real numbers are a one object category, also thought of as a one object category, and it's very nice. Okay, great. This also has a name, and it's called continuous time dynamical systems. In about 10 minutes, we're going to see how these interact. Okay, two more nice examples. I'm sorry, one more nice example. Anyways, we'll see some more examples. Okay, so here's one. B to the 0. 0 is the empty category. Okay, now how many functors are there from the empty category to there? And the answer is exactly 1. And so we have that. Now, we're used to this in arithmetic, okay? X to the 0 is equal to 1, okay? But this is not arithmetic, this is category theory. Okay, so that's an interesting thing that it works over. This exponentiation works similar to arithmetic. Okay, look at the empty category, look at B. There's exactly one functor, like from here to here, which doesn't take anything. It's called the empty functor. I don't know what you want to call it, but basically there's one object, and that's category. So it's basically this, with the identity morphism. Okay. So, by the way, this that works for numbers and also works for categories. So this is something called, and we'll see this much later, called categorification. A lot of times, rules that apply to numbers really are just small shadows of a more fundamental thing. This fact is more fundamental. This is about numbers, but this is a more fundamental fact about categories, and so we have that. Okay, so that phrase is called categorification. You take an idea in regular mathematics and you categorify it. You make it into a statement about categories. And of course, there's something called decategorification, which is something about categories, and you look at the shadow and you look at it as about something about numbers. Okay, great. On page, what page? On page 191, we have the following thing. Okay, it's called an important categorical idea. Okay, exponentiation is central. And the idea is as follows. If you look at the category b to the a, okay, it's fundamental. Okay, exponentiation shows up all over, and you're going to see why in a second. Okay, but there's nice ways of thinking about this. Okay, so you can think of a as the shape. In some sense, you can think of it as a shape. Okay, and you're looking at how shapes map into here. If you want, you can think of b as a context. These are just words you can use. It's a context. This shape, where is it taking place over here? So that's a context, okay? It's also called an ideal, okay? And in some sense, this is the word model, okay? So that's what we said. This is somehow the fundamental, and this is just an example of it, the model. By the way, mathematicians, logicians, and physicists use the word model in two exactly opposite ways. Okay, so the way I'm using it is, here's an ideal, here's something ethereal, not real. The model is absolutely the fundamental, an example of the ideal is the model. Okay, actually, the model is really one of these guys. Okay. Physicists use the word model the exact opposite way. So they have a lot of examples of things, and then they say, oh, let's model this as some ideal way of doing things. So they look for mathematical structures to model things, which is more of the ideal. It doesn't matter right now. We're going to have like this. I like to call this also A to be the cookie cutter. Okay, and then these morphisms from A to B, these functors from A to B, are really the cookies. They're what you want to get in some sense. I guess this would be the dough in this type of thing. Okay, another phrase is, this is the semantic model. Different phrases, we're just showing how these things work, but it is fundamental, it shows up very often. Okay, these functor categories are very important, so we ask the following question: to what extent is any category really a functor category? And the answer is something we're going to see in section 4.7 when we talk about the world-famous Monoidal lemma, is every category or locally small category. Those are things, those are technical things that we'll have to talk about when we get to section 4.7, but every category can be seen as embedded into set to the A opposite. So no, not every category is a functor category, but every category can be seen as embedded into a larger category or equal category that is a functor category. And so this is going to be very important for the Monoidal lemma, which shows up in a little bit. All right. Okay, great. So this tells you lots of examples, and we'll see more, of exponentiation. Question: how do these things relate? How do these different functor categories relate with each other? Okay, and so we have the following. We have two ways of talking about this. Let C be a category. Okay, and we have f is a functor from B to B prime. Well, then what we can talk about is a covariant. We're going to write that as f lower star. Okay, a covariant functor between functor categories. Okay, and if this is equal to hom of cat, C is fixed, F. Okay, C is fixed, F. Let me show you where this goes to. This goes from, C to the B, C to the B, C is the first thing, C to the B, to C to the B prime. Here's the prime. Okay, let me show you how this works. Okay, here's a typical element in here. A typical element in here is H from C to B. It's a typical element over here, okay? And what we're going to do is we're going to compose that B to B prime. Here's your F. We're going to post-compose with F. Here's your F. We're going to post-compose, and this map, C to B prime, is over here. So that's one way we're going to do things. That's an interesting way, okay? But there's something else. So this is covariant, very important, covariant. It follows, here you're going from B to B prime, here you're going from B to B prime, okay? But there's another thing. Let C be a category. And G goes from A to A prime. Okay, then we're going to have G upper star. This is contravariant. It's going to go from A prime to A. It's going to go the other way. Okay, and this is going to be equal to hom, in the category of categories. Here we have C is the target, and here's going to be G. And so this goes from C of A prime to C of A. In fact, most of the examples we're going to see is going to be this contravariant part, not the covariant part. Okay, basically what that means is we're going to be looking at how we're going to keep the context the same. We're going to see changing the shape. How does the cookies turn out differently? In other words, changing the shape of the cookie cutters. How does the cookies turn out differently? Okay, now we're going to see lots of examples of this. Okay, and again, so we want to see not just exponential, not just functor categories, but how the functor categories look. Okay, so let's do a simple example. Take the category 1, take the category 2, 0. Okay, and remember this is a category with two objects, two identity morphisms, nothing in between them. Okay, so we want to think of this as a one object category, this is a two object category, and we're going to take this from here to here. Now, we're going to go like this. Look at B to the 2, 0. That's another way of saying B cross B. Okay, and then this is going to be B to the 1. Okay, and this is, so we're going to call this functor S. So we'll call this S upper star. Okay, and what's this going to do? Well, if you have a functor from 2, 0 to B, okay, and you have this 1, you're going to precompose it with this. So this is an H. You're going to precompose it with it. Basically, you're going to get out an object in B. Which one? Well, since you're picking this one out, so this functor, this one object here is going to go to this one object here, which is going to go to what this is doing. So basically what this is going to do is project on the first element. So here you have two elements, 2B you could have pairs of objects, you're going to project on one of them, okay? As opposed to that, here's another example, 1 and 2, 0. Here's one object, here's two objects. We're going to have this go to here. Well, guess what? We again get a functor from b to the 1. We'll call this t for target. And so this is t star. And this is basically b of 2 to the 0, which is b cross b. Okay? And basically this is the second projection function. Okay, that's the second projection function. In other words, take a functor that picks out two of those things. This one is going to pick out the second one, and we're going to get that. Okay, great. Let's do another one. Let's look at 1 going to this category. Okay, we saw that category before. That's the shape of a graph. Let's make sure my camera is the right way. That's the shape of a graph. Okay, and basically that's going to pick out the vertex. So this one object here gets to there, picks out the vertex. Then look what we have. We're going to have b to the 1. By the way, what's another name for b to the 1? B. Okay, oops, sorry, not interested in arbitrary b, we're interested in set. So this is set, which is equal to set to the 1. Okay. And we're going to have set to the shape of a graph, and it's going to go this way. So, I don't know, what should we call this map? We'll call it, I don't know. I don't call it anything. I call it J. Okay, so this is J upper star. And basically what this is going to do is, it's going to take a graph which chooses vertices and, arrows and vertices. We're picking out the arrows part. And so this is going to be a forgetful functor that picks out the arrows. So take a graph and pick out the arrows of the graph. Okay? Okay. Of course, we could also go like this. And so then we have a forgetful functor that picks out the vertices. So that's two different examples of those things. Okay, great. Let's do another one. Take 1 and think of M as a one-object monoid. Okay, and so this map is the only thing it does do. It picks out the one object. So this one object goes to this one object. There's nothing else it could do. The main point is this has a lot of extra morphisms. This only has the identity morphisms. Okay, great. And what we're going to get is, here's going to be your category of M sets, and this is going to be set to the 1. What's set to the 1? That's just set. Okay, sorry, I'm not making my sets bold-faced. Okay, and basically what this is, let's call this K. So then this is K upper star, contravariant. And what this does is takes an M set, forgets all the operations on it, and just gives you the underlying set. Okay, all these different examples are basically forgetful functors. Okay, so we're looking at forgetful functors, but the idea is very simple. What you should do is you should think of all these extra things over here. One is the plainest shape in the world, and all these are other shapes that have more structure. And what you're doing is you're plugging the one in and saying, okay, I want this part of the structure, I want this part of the structure, I want this part of the structure, and you're getting the forgetful functor that only has that part of the structure. So that's a very nice thing. It's a very nice thing. Okay, but it's a little bit trivial because obviously we don't only want to look at one thing. So here's another example, and this is a very interesting example. Here's this. Think of this as a one-object category. Then you have the reals as a one-object category. And there's a nice inclusion. Good. Okay, now I want to look at the contravariant version of that. So this is set to the natural numbers, set to the real numbers, and we have a functor like this. We're going to call this ink upper star. Okay, good. Now, let's go through this. What does it do? This is dynamical systems, continuous dynamical systems. So they change continuously. You have states of the system and they're constantly changing. This is discrete time dynamical systems. They change 0, 1, 2, 3, 4. Now watch what this has. So pick a typical dynamical system that's a one object category that picks out a set with an uncountable many operations on them. Now, to get this thing, we're going to include this into here. Okay? And now we're going to get a map from here to here that's a discrete dynamical system. So we went from here to here. Okay, and what it does is, it doesn't want to know what every single thing is. It just wants to look at the whole numbers, the natural numbers that fits in there. We're not even interested in the negative numbers. So that's very nice. Okay, but I want to say something else. This is what science is all about. Seriously, this is what science is all about. You have continuous things constantly changing, always. Nobody looks at, there's continuous changes all the time. Okay, and what does a scientist do? He makes observations over time, and he says, oh, look, this is what happened at this time. This is what happened at this time. This is what happened at this time. So what you're doing is you're taking continuous thing and you're modeling it with what happens at discrete times. And that's exactly what this is all about. And the trick is to try to get information about this by looking at information about this. I looked at these events in these times. I want to know what it's all about. Okay, let me just show you one other thing, one other example. I'm not going to do it, but we do the following. I describe a map from the natural numbers to this. Oops, maybe not. Maybe the other way around. No. No. I describe a functor from the shape of a graph to the natural numbers. Okay, and then what we do is we go the other way around and we get set. Oops. The category of graphs and the category of discrete time systems, dynamical systems, and we go this way. Okay, and basically I show this in the book. What it does is, for every such thing you can describe a map that does it, just looking at the first map and the zero map. Okay, it's a little bit technical, not particularly interesting, but it's a way of bringing these cases together. Okay. Okay, so those are examples of how functor categories interact with each other. I want to do one more example and then we'll talk about common categories. And the one more example shows up very much in next class and shows up all about limits and colimits. And it goes as follows. Let A be a category. Okay, and just to keep our to keep the intuition going. So here's a typical element, here's a typical category. So we're going to draw a small one, A1, A2, A3, A4, and this has a map like this, and this has a map like this, and this has a map like that. Of course, there's identity maps, etc., etc. Okay, but I want to give these names also, F1, F2, F3, F4. These are the names of the maps. Very nice. Now, to every category A, there's a unique category, a unique functor to 1. Okay, so if you want, you can think of 1 as the one object category, and there's a unique functor that basically collapses all these down to this one point and this one identity map. Can't get simpler than that. Okay, but I want to look at here's B of A. Here's B of 1, which is another way of saying B. Okay, and I want to do bang upper star. I'm going to call this something which I've called many other things in this book, delta. Okay, and basically this is called the diagonal functor, but we've seen the diagonal functor where we were dealing with 2 elements, okay, pairs of elements. But now I want to just any category A. Okay, so let's see how this works. Okay, and the answer is this works very nicely. You're going to have a functor from 1. I'm sorry. You're going to have a functor from 1 to B, like that. Okay, that's going to pick out a certain element in here. Okay, and then what you're going to do is we're going to precompose that with a functor from A. Okay, now this is the unique thing here, and this is, let's say, any functor H. Okay, now what does this look like? That's a funny thing. So what does precomposing with this unique functor do? Well, what it does is, for every object here, little a, no subscripts, no superscripts, little a, it's going to go to the 1, okay? And it's going to go and pick out whatever that h did, okay? And so we're going to call this delta. I'm sorry. Nope. Okay, we'll call this delta. Okay, but the point is, what this will look like is same shape, but totally different. Not totally different, same shape, but different objects. This is going to be A, this is going to be A, this is going to be A. Instead of having A1, A2, A3, A4, it's going to be one object, okay? And the morphisms are all going to be the identities on A. Identities on A. Identities on A. Identities on A. Okay? Now, that's really one object. You can crunch that to one object, but I want you to see it as this. It's an example of this, where everything is, instead of having 4 different objects, you have one object. Okay? And this is called the diagonal morphisms. Okay? You generalize this A, this single A, becomes the whole shape, the whole diagram. Okay, and again, we're going to see this next semester, next section. Great. Let's just talk for a minute about comma categories. What's a comma category? Comma category is an interesting construction that does exactly what we saw before, namely it changes the morphisms of one category into the objects of another category. So let's see what happens. So what's this all about? You're going to have 3 categories, A, C, and B. And you're going to have 2 functors, F and G. Okay, so let me tell you what the comma category is. First of all, the comma category is written like this. F, comma, G. It's also written like this. F, down arrow, G. Okay, obviously comma category like that. We're going to write it like that. Okay, now let me tell you what these things are. Basically, they're going to be morphisms in here. So this is pointing here, this is pointing here. Basically, it's going to be morphisms here. The objects of the comma category are as follows. They are triples. A little object in here, a little object in here, B, okay, and a morphism, F. Okay, these are the objects. Let me tell you the morphism. The morphism is in here. Okay, so the main idea is it's an object in here, an object in here, and a morphism over here. So the object is, what's the relationship? F of A, that's a typical element in here. G of B, that's a typical element in here. B is here. Well, G of B is here. And the function is F from here to here. So these functors describe morphisms in here. That's what a typical element is here. Okay, and what's the morphisms? Well, the morphism from here to A prime, F prime, B prime is, you're going to have F of A prime, G of B prime, and F prime, okay, is going to be a map, okay, little g, where, okay, so what's the map? It's going to be a G where this is in A, and an H where this is in here. So this is going to be an H, I'm sorry, F of G, G of H, okay, capital G of H, okay, such that this commutes. So basically, you take the image of F, you take the image of G, and you see how they're connected in here. Okay, sounds a little bit convoluted, but we've seen examples of this. So let me show you a nice example. Oh, I'm sorry. Composition is putting one square on top of the other or to the right of the other. Okay, so here's a nice example. Here's a nice example. Set this to be 1, okay, and set this to be C, and set this to be the identity on C. Okay, now what does this do? This picks out a little element C in here. Nothing. Picks out one little element here. And what does this identity do? It does nothing. So it basically, whatever's here, it goes there. So what's a typical element here? Well, it's a C, and here's another one, C prime, and there's going to be a morphism from there to there. And then what's another element? It's going to be a morphism from C prime prime. And then what's another element? It's going to be a morphism like this. So it's basically the co-slice category. Okay? It's going to pick out an element here, and these triangles are going to be that. And I've said this before, when we talked about slice categories and co-slice categories, they make morphisms of one category into objects of another category. And so that's a special instance of this common category. We can also do it the other way, namely, okay, we can have 1 over here, we can have C over here, and we can have, this is the identity, and this is picking out one element. And then again, we have the slice category. So typical element will be, this G will pick out some element here. For any other element, you're going to have a morphism like that, and you're going to have commutative triangles like that. So slice categories and co-slice categories are special examples of comma categories. Okay, let's do another one. Okay, how about if I do this? C, C, C. Identity, identity. Okay, then the objects of the comma category are what? Pick a typical element here. We'll call it, I don't know, C1. Pick a typical element there. We'll call it C2. Do the identity of this, which is C1. Do the identity of this, which is C2. And now have a map like that from F from C1 to C2. Okay, that's an arrow. And then the morphisms, well, there's going to be a morphism in here. There's going to be a morphism in here. We're going to have this C1 prime. We're going to have this C2 prime. We're going to have a map F prime. Okay, what did we call this? Arrow categories. So slice, co-slice, and arrow categories are all special cases of comma categories. Okay, great. Okay. Okay, good. Now, we're going to use arrow categories. We're going to use them a lot. We're going to use them, not a lot. We're going to use arrow categories, but I want to show you how arrow categories get along with each other. Okay, and so we have the following. Let's say we have A is over here, and C prime. Okay, and we have a functor here and a functor here. Okay, and B is over here, and B goes like this, and B goes like this. Okay, close this up. We have an arrow category here. I'm sorry, I want to use the same names as I used before. FG prime. So this is FG, F prime, G prime. Okay, very nice. Okay, let's do this. You ready? This is an arrow category. Close that off. This is an arrow category. We have two arrow categories, C and C prime. Very nice. Okay, so far they have nothing to do with each other. However, if you had a morphism like this, a functor like this, H, such that this commutes and this commutes, both triangles commute, then you have the following. Then you have FG, that's a comma category. F prime, G prime, that's a comma category. And you're going to have this map, H, we'll call this H, it's induced by H hat. I'm sorry, H induces H hat. So if there's a functor from C to C prime, such that this commutes, such that both of these commutes, then you have a morphism between comma categories. Very nice. Hold on, we're not done. One more step, and again, we will use this, but it's nice anyways. Let's say we have not one, but two functors. A functor from there. I think it doesn't make a difference. We'll call it right. And we'll call this left. And we'll say you have an adjoint functors. Great. Okay, you have adjoint functors. Now, very nice. Here's the point. You ready? If this has to commute, and both of these have to be legitimate functors, I'm sorry, they both have to make both triangles commute, and so you have, this we'll call R hat. And L also has to have both triangles commute. And so we have L hat. Okay, and main point, if this is adjoint, then this will be adjoint also. So we have a way of going from comma categories to functors between comma categories to adjunctions between comma categories. And again, we're going to use this only once, I think. We're going to use it next section. When we come back, so what are we doing next section? We're coming back and we're talking about limits and colimits. So the whole chapter 3, we talked about limits and colimits, but we did it in a very ad hoc way. What we said was, if you have this shape, then this is the limit. If you have that shape, then this is the colimit. If you have, et cetera, et cetera. So we did it and we listed off products, coproducts, equalizers, co-equalizers, things like that, pushbacks, pullbacks, et cetera, et cetera. But now what we want to do is we want to revisit the whole thing, okay? And we want to talk all about limits and colimits, but from just shapes. We don't want to say what shapes we have. And so we're going to have this, okay? Okay, so this was a fun section about these different exponentiation categories. Have a great day.